This conference will now be recorded.
Okay, I believe I've missed the initial cue not to start talking before the record button had come live. But anyway, we'll move on. The agenda for today will be starting with sort of a general overview of the current state of play relating to decarbonising railways, referring to latest industry publications and trying to tie that in with the latter part of the presentation, where we'll be looking to apply the understanding of Tensor's rail bed trackbed stabilisation technology in terms of a quantified carbon assessment, where we can actively show what the reduction in the CO2 equivalent would be for adopting geogrid product systems within the trackbed in certain cases and scenarios. The summary will give a quick recap of what we've covered there, and then we'll open the floor to a bit of a Q&A session to yeah, I want this to be as interactive as possible. If you've got any thoughts or you've got any queries, then yeah, we can talk that through. An important one to start with, the Network Rail environmental sustainability strategies, and 4 key points identified there. The sort of strive towards a low emission railway, as we talk about electrification, battery powered chains and so on. A reliable railway that is resilient to climate change, flooding, the increased frequency of extreme weather patterns, no more so than the last week, 3 storms within a week. Obviously that has significant impacts on critical infrastructure, so that's certainly not going to be going away. How do we sort of deal with trying to minimise the future impact, as well as dealing with the case we've got on our hands at present? Improved biodiversity of plants and wildlife, a lot of information on this, HS2 particularly, where we're going through sort of corridors of rich wildlife. How can we replenish that and not just sort of provide an equal level? How can we actively improve it? An interesting one in terms of what we'll cover later, minimising waste and sustainable use of materials. This is a key part which we can get involved with from the onset of design, making sure that we're working collaboratively through the supply chain, so the designers, the contractors, the clients, the material suppliers. If we look towards some of the figures from Network Rail, 2.1 million tonnes of waste generated in 2018-19. Significant quantities there, but there's already very positive initiatives going on, and what can we do to minimise the waste in the sort of the initial design, and how can we look towards these full life cycle loops where we can reuse, recycle and make better. An example there, the ballast cleaning system, which has recovered 2.6 million tonnes for reuse on the track through the network rail operations over the last 10 years. So we may see high volume stated of the waste, but again, we can actively look to limit that and recycle where possible. The setting out of science-based targets as well, having meaningful targets to work towards it is important. We're all conscious of the achieving a net zero emissions by 2050. I think it's 2045 in Scotland. Yeah, the things are quickly going to ramp up, so we need to take action now. Linking this to the earthworks technical strategy, this it takes on from the sustainability strategy about the impacts of climate change. We're all aware of the change in weather patterns and the intensity of that over sort of more recent years. How can we make that more resilient? The critical infrastructure which we need to maintain. Prolonged wet weather, increasing poor water pressures, for instance, in clay slopes, washout in granular slopes, the seasonal shrink and swell a lot of these key parts which we can start to task with different types of trackbed or sort of embankment stabilisation technology. An interesting one there as well, when we start to potentially talk about modal shifts, taking lorry loads off the roads and putting them onto train tracks. Are we likely to see increased embankment traffic loading and tonnage growth as we sort of see the need to sort of add to what we've got with passenger trains? If we're going to have increased amount of freight, then we need to make sure that we're designing for that accordingly and can make that resilient. So we will touch on that again later in terms of how Tensar have developed our design method to take into account these variables. The PAS 2080, carbon management in infrastructure, is a critical publication in my eyes. The world's first specification for managing whole life carbon in infrastructure. It's certainly been discussed within the advisory committee I'm on, which Joe mentioned during the intro session. Some very important information and guidance on there about having meaningful reduction targets, baselines, quantification, so we can have some tangible sort of goals to work towards. An important feature of it, again, is having this collaboration through the value chain members, so not just through the asset owners such as the likes of Network Rail. How can we engage through from the designers down to the contractors, the people actually installing the systems, the material suppliers? How are we embracing innovation and adopting the improvements that are made in technologies? This can look to source low carbon materials from the onset, or essentially look to make benefits of leaner design methods, evolved design methods. The RSSB rail carbon tool, there's a variety now of different carbon tools available for general infrastructure projects, but the RSSB one being specific to rail. You can see now as part of the Network Rail environmental and social minimum requirements that it's sort of a necessary undertaking for a carbon assessment on a project with a net spend of over £1 million on civils, track or OLA. The projects must demonstrate that the results has subsequently been assessed and influenced the design and construction, reducing this embodied carbon and saving, leading towards the economical benefits as well. A standard input source of information for these would be the environmental product declaration sheets, which we'll touch on very briefly in terms of the data Tensar have available for input to these type of carbon tools. There's a lot of general information that can be put in, but in terms of product specific, this is the general requirement which we can share as a material supplier. Setting the scene, we'll now delve into rail trackbed stabilisation technology to sort of put into context where Tensar can come in and start to create benefits in terms of the trackbed construction. This is separated into two distinct areas in terms of Tensar's assessment of the rail trackbed. So we would, if we're concerned just with the upper ballast section, we would have a specific geogrid which has been optimized for stabilization of ballast aggregate particles. So the principal function there, the lateral confinement of the ballast, that lateral confinement minimizing the rotational movement of those ballast particles, which will limit the fouling of the ballast, but will also limit the ballast settlement, which will obviously impact the sleeper settlement, so we can extend that serviceable period before any maintenance tamping is required. Below that, if we're bearing onto we may well be bearing onto a competent subgrade, a stiff clay, sort of sands and gravel, but quite often there may be inclusion of a sub-ballast layer. which would generally be a sort of a granular capping sub-base type material, generally a more well-graded material, where it tends to have other geogrids for optimum interlock and confinement. The principal function there would generally be to provide a target level of support, a stiffness modulus, typically anywhere between sort of 45 MPa dynamic modulus, which are a common requirement as well when we start to look at potentially increased traffic loading, high axle loadings. We can have that provision of increased bearing capacity. They sort of set the scene for where the geogrid products will go within the trackbed construction, but they may have different functionality depending on sort of the nature of the project. We may have the need to increase the trackbed stiffness where we're going over sort of soft to firm crown conditions, which may need some sub-ballast improvements to support the upper trackbed. We may be wanting to extend the service life before the ballast needs to be potentially cleaned, so we can look at limiting that ballast degradation, which is more a recent development in terms of how we can assess the trackbed, reducing settlement, so we're extending the intervals between the maintenance, and then sort of more niche areas where we've got the smoothing of transitions, which geogrids are used extensively. So approach embankment to an overbridge, where we're going to have that change in stiffness as we go across the bridge deck. We've got approaches which can smooth that approach and subsequent boarding onto the stiffer section. We'll firstly look at the application of ballast stabilisation with an introduction to where the technology came from and how it's evolved over the years. So as highlighted in the earliest slide, the principal function is the lateral confinement of that ballast aggregate. We'll look into why that specific geogrid has been optimized for that type of ballast material. This would generally be employed during the maintenance, so where the line section has historically had issues with regular upgrades and need for maintenance every couple of years. We often see geogrids being utilised to extend those maintenance periods before we're needing to get back on site, shut down lines, and try and limit sort of boots on ballast where possible. The timeline slide here provides a good background of what we've done and how far that goes back. You can see some of the very early works back in 1986, where we had sort of small scale laboratory testing of geogrids with ballast. So in these conditions, we were using a typical 300 ml ballast with and without geogrid, and we're looking to see how that build-up would react to cyclic loading, simulating rail traffic movements. This was done over soft and firm subgrades, and the general benefit that was being shown there was a magnitude of around 4 in terms of the extended service life period between it reaching its sort of critical sleeper settlement limit. So we could see there was a concept there which could be sort of taken forward onto larger scale testing to sort of validate the performance of this type of technology. This was ramped up with British Rail in 1994, where a 40-ton rolling rig load was tracked along, simulating up to 2 million equivalent gross tons, and yeah, again, various build-ups with and without a ballast stabilisation geogrid utilised. Similar benefits shown to the small scale trial work done in Canada. This time the so the benefit was trying to simulate how a geogrid over a softer subgrade could be comparable to a build-up over a firmer subgrade. So the general outcome of that was that a geogrid over a softer subgrade provided equal or similar performance to a non-stabilised build-up over a firmer subgrade. So again, you can see the focus of this was towards weaker ground conditions where this geogrid could be utilised more effectively. The largest piece of research we've done within this area was led by the University of Nottingham, which we'll go into a little more detail on. This was a 3-year project between 2003 and 2006. Part of this was funded through the Mercer Senior Grants, so the original pioneer of geogrid technology and where Tensor originated from. So there was a £250,000 grant which went towards this work. You can see the structure of the test there, starting off again at very low level tests to try and identify the optimum geogrid before putting that forward into larger scale tests before being employed onto a full scale site trial, and then trying to develop design methods from that. If we look at the typical grading of a ballast aggregate, we can what we were able to do then is look at different aperture sizes of the geogrid to see under small scale cyclic load tests how these geogrids fared and what the optimum material properties were. What we found from the aggregate gradings was that the optimum aperture size correlated to around the sieve size, where 50% of the grading was passing, multiplied by 1.4. As we can see by this sort of neat curve here, we can see geogrids with apertures that were too small didn't allow that effective interlock, whereas where the apertures got too large to effectively provide that interlocking confinement, then the performance dropped off again. So we found this optimum aperture size, which is where the large aperture originates from for use in ballast stabilisation. Once we had this, we were then able to take a single geogrid through to larger scale testing. So the railway test facility, which had, I think it was a setup of 3 sleepers with 3 load actuators to simulate the rail traffic to quite significant number of loadings, so up to 1 million cycles. Again, from our very early laboratory test back in Canada to the work we did with British Rail and now onto this larger scale, we can see, again, similar type of benefits there. So the service period by using the geogrid was extended by around 2.5 times before it was starting to reach the sort of the critical settlement limit for the sleeper, which I believe it was around 6 millimetre. Once we'd sort of again proven the benefit of the geogrid within that increased testing, we identified together with Network Rail a suitable section on the West Coast Main Line where we could sort of apply it at a larger level with control sections which could be monitored along with the stabilised sections. So this was up in the northwest around the Wigan area. If anyone's familiar with there, Coppell Moor, there had been issues with this particular section, and it was getting towards a point where the frequency of the maintenance was leading to a requirement for a full reconstruction of the main line. They had the ability to use the high-speed track recording coach. So again, we could have significant data fed back over regular periods, so we could start to really build up a good level of data on how the products were performing in service. You can see the section of line there, where we were looking at maintenance schedule being applied every, I think what we can see there, a couple of times a year in certain phases. Once the installation of the geogrid had occurred, we've got beyond sort of 3-4 years before it was reaching anywhere near the need for it to be maintained and sort of have any work done to it. So again, keeping boots off ballast, and the client being particularly happy with how poor the sort of the previous works have been going. So again, taking that forward, we were able to demonstrate on an active mainline project that the geogrid worked effectively, having greater effect over softer subgrades due to the greater ballast settlement. And we were able to then take forward this into a formalised design method, which is still active today from the design curves you can see from the 4239 standard. We can see how this was incorporated here, where taking those principles of a geogrid over a softer subgrade, providing a similar level of performance to that over a stronger subgrade. You can see from the 4239 standard here, for existing lines between 50 and 125 miles an hour, you've got the option with and without a geogrid reinforcement. So we're allowing for a lower sleeper support stiffness, which correlates with a lower formation stiffness, but we're able to, as what we've shown through the sort of the past research and development, that we will provide a similar level of performance. If we read off the curves there to give an understanding of what the impact of that would be, we can see if we're designing it for that 60 kilonewton sleeper end stiffness, we've got a build up of around 550 mil for the case shown there. I think the 20 MPa subgrade modulus compared to 370 mil for the same with the geogrid build up. So we're saving in the region of around 180 mil of thickness there of the sub-ballast. So that's limiting potentially the import of the capping sub-base material, as well potentially the limiting the need for disposal of unsuitable subsoils during the excavation. Back to the timeline. So taking that forward from 2007, where the invent of the tensile triaxial technology came in, we further developed this technology using a different geometry of geogrid to provide enhanced interlock confinement and a stabilising effect. Work was done to quantify this improvement with the Czech Technical University, where we've got a number of past research works with, which was again demonstrated a betterment over our historic biaxial geogrid technology. More recent work in this with the Penn State University in America is looking at this smart rock technology, so 3D printed ballast particles with accelerators in, so we can actually monitor how this stabilisation effect of the geogrid can limit the rotational movement of the ballast and the subsequent breakdown degradation of the ballast itself. For the ballast stabilisation product, we've got the network rail approval for the Tensile Triax TX190L product, and importantly, relating to this presentation, the subject, we've got the environmental product declaration, which can be fed directly into the carbon calculator tools. So this is an independent product declaration sheet, which covers the embodied carbon of the product itself. It's obviously a manufactured plastic product, which has a quantified carbon impact, but it's the benefit, the associated benefit of that, and the longer term, which will show the benefits. On to sub-ballast stabilisation now. So moving down through the trackbed layers. As I mentioned previously, our general approach for this is to design the sub-ballast to achieve a target at the formation, so the base of the ballast layer. So yeah, typically that would be the dynamic modulus or the EV2 static modulus, and we've got experience of that not just within rail, but sort of within other general applications. That's one approach. Or again, if we're aware of the sort of high axle loads of the train vehicles, then we can start to model that potentially through finite element analysis to see what the loading deformations may be. We have the mechanically stabilized aggregate layer with the increased strength support, which can provide a benefit there. A similar timeline, this time looking specifically at sub-ballast. A lot of our early works, and it's still what we look at now on some projects, is simply providing this target level of support stiffness. It's an established design approach which we've got, but there are a number of variables there. So the achieved target level of support stiffness can vary depending on the quality of that granular fill, the weather, and the compaction regime. So there are a number of variables which we just need to be careful we cover with any sort of guidance we provide there. So a lot of this work was initially done across Europe, where again this EV2 stiffness modulus has found its way across onto the network rail design standards. We've got significant experience of providing these type of solutions across Europe through our global design offices. With the invent of triax, again, we work not just at using geogrids within the ballast, we introduced that within the sub-ballast layers as well, trying specifically for new construction. If we can keep the grid as low down as possible, then we can sort of limit any conflict with sort of future maintenance, tamping, etc. We also did work the Heriot Watt University looking at high-speed rail ballasted track, so not related to HS2, but sort of general high-speed rail projects, which again showed benefits of having this stabilised aggregate in terms of the high cyclic loads from the speeds of the train. More work again with the smart rock technology, which we'll cover in the later slides. Before a very brief intro into what we can do in terms of modelling this in finite element analysis. I mentioned in terms of providing this target level of the stiffness modulus. If we relate that from the 4239 standard onto the 2102, you can see the relationship there, and what we're comfortable with designing at Tensor from our works through other global design offices is designing for this EV2 static load modulus. So if that's a requirement, we can simply work towards that with the relevant guidance, and then we can work from established design curves and show with and without the use of a Tensor triax geogrid what the build-up thickness would be. A typical reduction over sort of soft to firm ground is sort of in the region of around 200 mil stone thickness, which will be used in one of the later examples in terms of the quantified carbon assessment. Back to the timeline. So we're now looking at this smart rock technology, which there's a really good video on this, but I don't think it potentially work too well on here in terms of buffering. So if anyone's really interested on that part of it, then feel free to get in touch with me, and there's a lot more information and videos which I can share on this. So it's basically 3D printed aggregate particles, both sort of ballast size and sub-ballast size, with these accelerators built within them, so similar to what's on your mobile phone device. So it can very accurately detect movements, rotational movements, and so on. So it can see how these are being affected through that stabilizing effect of the geogrid under cyclic loads, simulating rail traffic movements. You can see within the build-up section there where the smart rocks were included, so both within the ballast and within the sub-ballast. We've done various trials with this. You can just about see from that, as we increased the load of the cyclic loading, you could see the increased deformations with and without the use of the geogrid. and this also showed the improved performance when using the triaxial geogrid with its hexagonal geometry against that of the historic biaxial geogrid product, so showing improved performance and increasing the service life. This one probably takes some explaining. You can see, so if we look, if we look at the sub-ballast section on the right hand side, we can see under the initial lightly loaded cyclic, I think it's 85 kilonewtons, we can see very minimal movement of the aggregate particles. As this increases up to 135 kilonewton cyclic loadings, we can see that there starts to be some rotational movement of the aggregate itself. Without any geogrid, where we can see the black outlines there, we can see significant movement in terms of the rotational movements of the ballasted particle. Whereas when we start to introduce a biaxial geogrid or improved by the triaxial geogrid, we get a much reduced rotational movement range. So again, we're linking this to limiting the degradation, fouling of the ballast or the sub-ballast material, which is part of some ongoing work we have. Very brief intro into the new design method which we're slowly introducing. I mentioned from the extract from the earthwork strategy about taking into account of the potential increased loadings on embankments and the subsequent stability of those, but as well how that affects the trackbed construction. So if we're used to dealing with say 100 kilonewton axle loads and we're increasing that to 250 or even beyond, then that will have an impact on that trackbed. So we may need to ensure that we need to stiffen that up or make sure we've got sufficient strength to limit the deformation, the settlements of this sleeper. So we've developed design methods to not just look at the overall gross million tons of traffic, but we can actually break down to see through different loading axles and number of repetitions how that will affect the serviceability of the trackbed construction. That will relate to a performance-based design where we're limiting the plastic subgrade deformation as well as the progressive shear failure, so we can work within serviceable limits for that, and can be subsequently modelled in an FEA programme using the Tensar soil stabilised model. This was covered in much greater detail. I think this was about a 40-minute session in itself, covered by Andrew Lees, our head of technology. If this is of interest, then yeah, we can arrange a follow-up session or contact me and I can share relevant papers on the subject. This does open itself up to much more sophisticated type design analysis to what we've historically done, and when we start to look at transition details and so on, we can potentially variable subgrade soils. We've got the ability to now model this more accurately and effectively. The value proposition which this allows us to look at then is that we may have a conventional build-up which is looking for a value engineered design. Are we looking to provide the same amount of serviceability and providing the lowest installed construction costs, so reducing the thickness of the sub-ballast layers to achieve the same performance requirements? Or are we looking to actually extend the service life of this asset, so we're not actually reducing any stone construction, but we're going to extend the service life of that asset by 2 or 3 times of that without? So we've got the options which we can talk through with the client, the contractor, to make sure we're hitting the right notes. Now, applying what we've learned about the trackbed stabilisation technology, Joe mentioned early on that Tensar have developed our carbon calculator over a number of years with input from industry, so we're taking in figures from main contractors, clients, and working out what we can actually offer the industry that is meaningful, not just a square metre price for a geogrid. We can actually show what the time reduction may be for installation of these systems compared to traditional, or we can start to show what the quantified carbon reduction will be. That might be more difficult for certain areas, such as smoothing transitions, where we're not generally looking to reduce the stone build-up as such, but in certain areas where we can either limit the frequency of the intervals before maintenance, or we're simply reducing the thickness of the sub-ballast layer, for instance, then we can start to provide a quantified assessment. For this example case here, we've got the project site in Leeds, which is around 100 kilometres away from our manufacturing site in Blackburn, Lancashire. The granular fill that was going into the site is estimated to be around 30 kilometres away. We're assessing a kilometre of track, which is approximately 4 metre width. The traditional build-up is 500 mil sub-ballast. What we've been able to demonstrate with using the Tensar Triax geogrid is that we can reduce that thickness by around 200 mil. If we run that assessment through, we can see by reducing that 200 mil of stone thickness, we've reduced the volume of granular fill by around 800 cubic meters, which corresponds to about 2.6 tonne there. If we look at the carbon footprint of the quarrying operations and compaction operations for the installation of the sub-ballast material, we can see significant reductions there starting to come through. We obviously have the additional element of the geogrid component itself, which will be taken from the environmental product declaration. We take into account the transportation of the granular fill, both sort of full as it's arriving on site and empty on the way back, and as well the transport of the geogrid itself. When we evaluate all that using sort of industry data on that, we can see for this specific example that we're saving around 39% in terms of the embodied carbon. Important to note on this one, this is considering that the construction is from grade. So if we took into account potentially the saving of 200 mil excavation of the unsuitable subsoil and carting away off to landfill potentially, or onto a neighbouring site which may be a little distance away, then that 39% value may well extend beyond 50%. So again, in the right scenario, there's significant carbon savings that can be achieved. The Tensar Triax geogrid full product range has the environmental product declaration. We're currently in the process of upgrading from cradle to gates to cradle to grave, which I believe that should be in place by around May or June this year. So yeah, sort of pushing the boundaries in terms of the requirements to demonstrate the full life cycle of the product. This is the standard input source of information to a variety of carbon calculator tools. Yeah, you can either contact me or through Tensar's website, and yeah, this isn't secret information, it's freely available. What this will do now as well, the upgraded EPDs is include the benefit of our manufacturing facility in the UK, sourcing 100% renewable electricity, and there's some ongoing improvement works there to limit the embodied carbon in terms of our product. Pulling this back to one of the early slides, the rail carbon tool, said that this is a sort of statutory requirement that project value of over £1 million spend should be carrying out these carbon assessments, and then the sort of the findings of this influencing the subsequent redesign and construction. So yeah, we certainly have that capacity to input and start to show savings on these projects. Finishing off now, yeah, hopefully it's come across that the Tensar trackbed stabilisation technology has been extensively researched and developed with a number of proven applications. where we can come in for decarbonising the trackbed build-up is limiting that trackbed layer thickness and subsequent excavation and disposal of subsoil materials, extending the service life, reducing maintenance intervals. We would love to share more data on that one, but we need to work close with clients and designers to get some more meaningful data so we can start to quantify what the carbon reduction benefits would be there as well. But all of this, again, we've got the constant source of information for the grid component coming from the environmental product declaration. Tensor, in terms of our UK operations, we're risks verified, not just for the supply of the product systems, but also our design services, which are audited annually. So if Tensor are required to take design responsibility and sort of develop this carbon reduction proposal, then yeah, we have the capacity to do that. And just throwing this one out at the end, I believe that this will be going out as an email from the PWI as well. It's been a little while since we've sort of opened up the UK manufacturing facilities now, due to obviously the sort of recent events. We did this with Network Rail a number of years ago, and we were keen to offer this to all the PWI members. So the current dates we're looking at towards sort of middle end of May, the 19th to 20th of May, up at our Blackburn site. If anyone is interested, then yeah, we will be providing a tour of the manufacturing facilities, and yeah, so just some general hospitality, a bit of food and drink, and yeah, a bit of a presentation, some of the videos on the smart rock technology, which we covered earlier. So feel free to get in touch with me either directly, or there should be an email going out soon as well. Okay, so yeah, that's me, Joan.
Fabulous. Thank you very much, Peter. So just to ask about the tour, I presume that spaces would be limited on that. You can't have unlimited people.
Yes, that's right. So it'll be first come, first served on that one. So yeah, we can either do it on Thursday the 19th. If we've I think it's 15 we can do on a day.
Okay.
So yeah, we could do that over a Thursday and a Friday, or again we can maybe do a date a couple of weeks, couple of months after that if we do get a lot of interest.
Okay, all right, thank you. So obviously everyone listening on the call, if you're interested, get in contact with Peter and put your name down. Thank you, Peter, very much for a very interesting presentation indeed. So we've got a few questions here in the chat box. So I'm just going to really ask the people if they would like to ask their questions themselves. So the first person I'm going to call on is Richard Hill. If you're still here, Richard. If you'd like to unmute yourself. Perhaps not. We'll come back to Richard. I think Payman has left, but the question was how much is the service life of geogrids, and also is there any optimum geogrid level in the ballast depth? Well, I think you've sort of explained that one in the presentation, but maybe just to recap on it. So the first question is, how much is the service life of the geogrids?
Yeah, so it's typically 100 years with the Tensor Tri-X geogrids.
Okay, thank you. And then Richard's question was similar. What is the service life of the embedded modular devices?
Of the embedded modular devices?
I think he means in the ballast, the ballast.
Oh, sorry, the smart rec technology. Yeah, but that's in a laboratory facility, so that's never gone on sort of a rail facility. I'm not sure on that, but yeah, I don't think it would be robust enough to have for more than a couple of years.
Okay, thank you. And then is Sankar, sorry, does someone want to say something?
Yeah, I was going to say that there is some aside research work going into the monitoring devices within the geogrid to look at the long-term performance of ballast. But yeah, that was probably a separate subject in itself.
Okay, thank you, Peter. And then Sankadev, are you still there? Would you like to ask your own question?
Hi.
Hi.
Hi, Matthias. My question is do you have some evidence where geogrids have been used in ballasted track, which is inside boat tunnels? And if, like you have given some evidence of a reduction of settlements in ballasted track on open grounds on subgrade, do you also have similar evidence for reduction of differential settlements in the track when the ballast track is inside a boat tunnel and the tunnel has settled and the geogrid has saved the track?
Okay, yeah, I can understand the application. Yeah, we don't have specific data from that type of scenario, unfortunately. But yeah, I can see sort of the general principle being maintained there.
Okay, thank you, Peter. Thank you. And then Kuyar, are you still there?
Hello, yes, I'm here. Thank you very much for the presentation. My question is about the maintenance, trackbed maintenance. Does it have any limitation during tamping or stone blowing if the geogrid is just affected by rupture or the failure? Thank you. Yeah,
so the geogrid would typically be sort of at the base of the ballast, so 300 mil below. So yeah, where we've got the sort of the reconstruction, where we can get the grid lower within the sub-ballast, there obviously won't be any impact there. But yeah, in terms of the ballast being positioned, typically a minimum of 300 mil below. Yeah, we've not had any sort of issues with that from what I'm aware.
I guess the other important thing is, Peter, once it's installed, people need to provide appropriate health and safety file information about the depth that it's been laid at, so that it's clear for future maintenance what's possible and what's not. Yes,
that's one of the key points, it being recorded that what has been installed is known for sort of the future sort of service operators.
Yes, because in my experience, I've certainly known about not this particular geogrid product, but other similar products getting stuck in a ballast cleaner. It has happened. So yes, it's a very good question. Okay, then a good question. Is that you, Rob McDonald?
Yep. Hi, Joe.
Yeah, would you like to ask your question?
Yeah, it was just about the material, really, regarding I think it's HDPE plastic that geogrids are made from. It was just, are they made, or can they be made from recycled plastic waste?
Good
yes,
question.
The geogrids are made from polypropylene for the Tensar Triax and historically the Biax products. There is work being undertaken at the moment. In terms of the geosynthetics sort of product standards for a permanent application, the geogrid can't be sourced from recycled polymer at present, but there is work being done on that to sort of loosen this. So for where the geogrid would be applied here in a permanent application, at present it would be for a virgin polymer material only. But yeah, probably as much as I can say now is that yeah, there's certainly work going on into that at the moment.
Okay, thanks, Peter. That was a very good question, Rob. Right, Shoaib, are you still here? Not sure. So the question was, what are the minimum? Oh, you are here, right? Sorry, carry on. You asked your question.
Can you hear me?
Yes, perfectly.
Hi, Peter. A good presentation, by the way. So my question is, obviously I've got a question from technical side. So what are the minimum depths in millimeters between ballast and subgrade ballast? Is there a maximum depth that you can lower below subgrade? So as you're coming down to subgrade, obviously there's a depth. There's always a minimum and a maximum depth, but can you always lower? Is there a certain maximum that you can lower below ballast? If that's clear.
Yeah, so say if you're over particularly poor ground, you potentially need a greater thickness of sub-ballast. So you're saying what the maximum depth of that could be in our products?
Yes, indeed.
Yeah, that's it. So the stabilising effect of the geogrid. So again, I've kept it quite brief today. The geogrid is applied sort of horizontally, so it's laid out horizontally, but it has a vertical stabilising effect. The vertical influence is around 350 mil. So if we were looking at a single layer of geogrid within the sub-ballast, that would be around 350 mil. But quite commonly, for when we do piling platforms, crane platforms, we'll often have 2 layers of geogrid within maybe 700 mil thickness. So yeah, there isn't a minimum thickness as such, but you may need additional layers of geogrid to maintain that stabilised aggregate mass. And
just to add on that sand blanket, now that you might know what sand blanket is, but from my point of view, I might. So why would you normally need a sand blanket within a geogrid? I mean, is there a specific purpose of that?
So yeah, that'll be primarily for the drainage, wouldn't it? So yeah, the geogrid would be providing that stabilising effect. So yeah, with an appropriate geotextile, which the geogrid may well be laminated with that. There are products out there which can remove the need for the sand blanket. You've got the I'm trying to remember the name of the product now. Is it the Hydrotex products, which can be used in combination with the grid to remove that sand blanket layer?
Perfect. Thank you so much, Peter. A great presentation. Thank you.
Thank you.
Great, good questions. And then just some comments in the chat here, really. One from Levente. He just says, regarding the question about the optimum depth in the ballast layer and the interference with track geometry maintenance machinery, we only recommend ballast at the bottom of the ballast layer. Yeah, so it's all the same thing. You've got to know what level that's at, where you've put it, and record it.
We did work on introducing the grid mid depth within the ballast and then at the base of the ballast, and there wasn't shown to be a significant change in performance. So we would always advise at the base of the ballast. Yeah.
Okay. Thank you, Peter. So I think that's the end of the questions. Just a nice comment there from Callum Richings. Hello, Callum. Nice to see that you're on the call too. Hope you're all okay in the Network Rail TBI team.
Yeah, we're good. Good. It's a surprise I didn't see your name when the presentation started.
Good. That's all right. That's good. Nice to hear from you. You're all still there. Right. Okay. So Peter, that's the end of the presentation and the end of the questions. Thank you very much, everyone, for your attendance today. Very, very good attendance today. Next week, just to let you know, we've got a chat from the RSSB giving the presentation at Chelsea, and that's all going to be some of the subjects that Peter touched on there about their RSSB Rail Carbon 2, but also lots of the other projects that they are involved in the world of decarbonisation, climate change and sustainability. So that should be quite another interesting presentation. So hopefully you can make it next week. Thank you very much once again, Peter. Much appreciated your time.
Yeah.
Have a good week, everyone.
All right.
Thank you.
Cheers now.